and I am recording. So what we're going to talk about today is kind of one of the major operations that we can do in calculus. It's called the derivative, but you already know what it is. It's the same thing as the instantaneous rate of change of a function. If you remember, we talked last time about using the slope formula to find the slope of a secant line between 2 points on a curve. And now all we're going to do is for instantaneous rate of change, and we kind of practiced this a little last time, we're going to get those 2 points to get closer and closer and closer. So if you think about it, the slope of a secant line between 2 points approximates the instantaneous rate of change at a single point on a curve. How does it do that? Well, it does that by getting the 2 points as close as you want them to be. Okay? I'm going to start this time. I'll start by sharing sharing my browser with you just to show you where we are in the course. And again, we're in week 3 of the week 3 activities we're going to do today are the derivative. Okay, and I'm going to be using these notes right here, the derivative notes. So if you want to open them in another tab or print them off, that'd be great. What I'd like to actually start with showing you is down here in supplementary material. Okay, I have, actually, I thought it was up here. It's actually in the week prior. Okay, I've got a derivative plotter that I'm going to open later on. And I wanted to point out this factoring calculator because I've gotten a couple of questions from folks where you're trying to find a limit algebraically, and I think you might be getting stuck with the factoring. Okay, so this is an actual app that if you type in, say, a polynomial equation, it'll try to factor it for you. Okay, so if factoring's a little rusty, don't get stuck there. Okay, make sure the calculus stuff makes sense. So I'm going to go back up to week 2, and I'm going to show you the slope of a secant line applet that we kind of looked at before. And I just want to show you what it is I'm going to be talking about, just so you have a mental picture of it. And again, you have these links, so feel free to play with the apps, okay? So here I have a green quadratic curve. You can see it's f of x equals x squared. The red line is a secant line between these two blue points. And what I can do with this app is I can move these 2 points closer and closer. Notice what's happening to the secant line. It's moving outside the curve, okay? And as it gets, these 2 points get closer and closer, this secant line approximates a tangent line at a point here, okay? So if you think about secant line, you're going to use slope. And what we're going to do with the tangent line is we're going to take the limit of that slope as the points get close to being the same point. In other words, as the distance between them approaches 0. Okay, so that's kind of why we needed to learn about limits before we learned about the derivative, because what we're going to start with is the slope of a secant line, which you all know how to use the slope formula, and then we're going to take the limit of it as the distance between the 2 points approaches 0. So that's kind of an overview of what we're going to do, all right? I'm going to start by sharing the notes, okay, with you. So give me a moment. That takes me a minute to get that up on my tablet. And again, let me open the chat just in case folks have questions. Again, feel free to unmute yourself and ask, or if you've got questions, you can type them in the chat. And let me just share this content with you. Okay, so everybody should be able to see derivative notes. Okay. And again, this just kind of recaps what we did last time. We approximated the slope of a tangent line at a single point with the slope of a secant line between 2 points. Okay. So again, just to review, all right, let's say we want to find the slope of a line that's tangent to a curve, and the simple curve, f of x equals x squared, kind of like I had open in that secant line applet. But suppose we're interested in it specifically at the point 2, 4. So what's going to be relevant here is the x value 2. Okay, here is a drawing exactly like what we just looked at with the secant line applet. Okay, and so what you want to imagine is here's the point 2, 4, and you will want to imagine another point that's h units away from 2 on the x-axis, right? So if we take the 2 plus h, which is our new x value, and plug it into our x squared, we're going to get that here, all right? And you can see this distance is going to be the difference between this point up here, which is at 2 plus h squared, minus the 4. Okay, that's the distance. So 2 plus h squared is the value of this point up here, the y value. Okay, see it? Right? And the distance here is going to be the distance between 2 plus h squared and the 4 that's down here. Okay, so the numbers or the expressions that are on these arrowed lines are distances. Okay, so again, what you kind of want to imagine is this is the point 2 plus h and 2 plus h squared. Okay, that's that point. And this is the point down here. I think you can see that on the graph is 2, 4. So the distances we're calculating are the distances first between the x values. Okay, so this distance is going to be 2 plus h minus 2, which is just h. Okay, and this distance is the y value of this point, 2 plus h squared, minus the y value of the other point, 4. Okay, so we're showing you the sides of a right triangle, so you can kind of see what we're doing. Okay, this isn't calculus. This is kind of introductory algebra, wherever you first saw distance in the Pythagorean theorem. Okay, so let me understand the picture. Okay, and you can see this stuff live on that applet, the secant line applet. That's what all the delta business was that you saw moving whenever I was sliding the point. Okay, so I'm just stopping to ask, does the picture make sense? Okay, so here's what you want to think of. Okay, let's call this point x2, y2. And let's call this point over here x1, y1, right? Got 2 points, and I'm trying to find the slope. y2 minus y1 over x2 minus x1. I think everybody remembers the slope formula from before. So here's y2, my y2 value. Here's my y1 value from that point over there. Here's my x2 value. Here's my x1 value. Okay, so that's just the stuff going into the slope formula. This is the plain vanilla slope formula. This isn't anything weird. Okay, so we haven't done any calculus yet. Okay, I'm trying to make this as familiar to you as possible. So if it seems strange, it's a good time to ask questions, okay? This should be super familiar. And if it's not, you probably want to ask some questions, okay? So what is strange is this concept of, well, wait a minute, doesn't this point have a number value? Yeah, sure. But the problem is I can move this point down the secant line, okay? And the h value changes, right? As I move this point down the secant line, h is getting smaller and smaller and smaller because it's getting closer and closer to 2, okay? So rather than put in a million different values, and we'll try it with a couple of different values, it's better to put the variable h in there, and then h can be as small as you want it to be, okay? So let's see what this does to our slope formula. Okay, so over here, the first thing I'm going to do is expand this binomial. This is just a FOIL problem, if you remember FOIL. Okay, so 2x plus h times 2x plus h. Okay, that's going to give me this trinomial here. Okay, so the 2x times 2x is going to give me we have a problem. Sorry. There's a problem with that. Let me just rewrite it. Okay, my bad. Okay, so this is going to give me 4x squared. Okay, then I have 2xh plus 2xh is 4xh. The x's dropped out in the example. So let me just do it up here. H squared, and I'll fix the notes, don't worry. Okay, and on the bottom, I have 2x plus h. It's basically, it's 2 plus h. There should be no x in it. That's the problem. My bad. I'm trying to figure out where the problem is. The problem's right here. Let me just get rid of it. Okay, here's the problem. It should be 2 plus h, not 2x plus h. Okay, so the graph is correct, and I just fat fingered it when I typed it in. So there should be no x's in here, because this point isn't 2x, it's 2. All right? And now when we FOIL, I get 2 plus h squared, which is 2 plus h times 2 plus h. And that's going to give me this trinomial. So 2 times 2 is 4. Positive 2h plus another 2h and h squared. Okay, everybody remember foiling a binomial? Okay, so basically that's where this comes from. And then I have the minus 4 from my y1 point. Okay, so let's take a look at your numerator. You see you've got a positive 4 here and a negative 4 here. Those are going to cancel out. And you're going to be left with the 4h plus h squared in the numerator. Okay, everybody's comfortable, I guess, with 2 plus h minus 2. The 2's cancel out, and I'm left with the h downstairs. Okay. So again, the only mistake over here in the algebra parts is this errant x. X should not have been in the expression. So if you just blob it out, then you're right. Okay. So then I have 2 plus h minus, right, 2 on the bottom, and then 2 plus h squared minus 4 on the top. So I'm just taking these distances. Here's the change in y. And here's the change in x. Okay, so I'm just putting those in there. Again, I apologize for the typo, but sometimes it happens. Okay. Everybody comfortable with where we are so far? Okay. Everybody should be good with us getting down here. All right. So again, let me just stop and ask, especially since I made a mistake there. Anybody have any questions so far? Just give me a shout out, yes or no. Are we good? Or do we need to explain some more? No questions? Okay. If you could all shout out yes or no, we're good. Okay, good. Just need to know. Okay, then. So we have this expression for the slope. All right. And now you can see, hey, look, every term in this expression has an h in it, so I can factor an h out of the numerator. Again, remember, factor means divide. So 4h divided by h leaves the 4. H squared divided by h leaves an h. And now I can cancel out the common factor in the numerator and in the denominator. That leaves me with the expression for the slope. Well, the slope is 4 plus h. And what's h? H is however far these 2 points are from each other in the x direction. Okay, so that's the slope of the secant line through these 2 points. And as h gets smaller and smaller, you can see this slope approaches the slope of the tangent line to the graph of f right at this point. Okay, remember as we moved this point down the secant line looked like it moved out and became a tangent line. Okay, a tangent line touches at 1 point, the secant line goes through 2 points. Okay, and I'm sure a lot of you are looking at it. I'm not sure what that is. A lot of you are looking at it saying, yeah, well, it looks like the slope is going to be 4. Okay, and you're probably right. Okay, because again, h is going to get smaller and smaller and approach 0. Okay, so how do we write that? Well, we can write it as a limit statement. Okay, so the slope of the tangent line at 2, 4 is the limit as h approaches 0. And again, this is an artifact of my equation editor, that it puts this as h approaches 0 sort of to the right rather than underneath. Okay, it's the same thing as the limit as h approaches 0, right, of 4 plus h. Okay, so you can see there's no problem with plugging in a 0 for h, right? And you can see that that becomes 4. Okay, so we're just directly substituting that 0 in, okay, for h. And you can see, oh yeah, hey, as I get right down to this 0.24, the slope of that tangent line to this curve is exactly 4. Okay, now what you just figured out, or what we just figured out together, is the derivative of that function, y equals x squared, at the point 2, 4. Okay, so the derivative of a function at a point, okay, it's the same thing as the instantaneous rate of change of the function at that point. It's the slope of the tangent line to the function's graph at that point. And it's also the marginal value of the function at that value of x. Okay, so these are all vocabulary words, okay, vocabulary words that mean derivative. Okay. Okay, and the derivative is a calculus thing. How come? Because we had to take a limit. All right. Now, what we're going to talk about today is sort of a manual way to do it. We're going to do the slope formula, take the limit. We're going to do an awful lot of approximating, okay, so you can see what's happening as h gets smaller and smaller, okay? So we're going to do a lot of approximating, and then we're going to do some algebra with exactly this formula here, okay? And so what I want to kind of encourage you is, please don't think it's all going to be that tedious. It's not, okay? What we're going to start introducing next week are quick, well, patterns for doing a derivative quickly, okay? So it may seem that what we're doing today is tedious and long and drawn out, but it's just to make sure you understand exactly how we're getting these values for the derivative, okay? Now, another thing I want you to understand is, before we move on, and I'll put it down here, the derivative of a function at an x value. Whoops, getting a little bit weird here. Get an x value. It's a number, okay? It's a slope, right? It's the slope of your tangent line. The derivative of a function in general, right? And we'll talk about that next time. In other words, if I'm not saying at a particular x value, is also a function. Okay, so what we're going to be doing today is we're going to be approximating the derivative of a function at a given x value. So we're going to be finding the slope of a tangent line when x is 2, the slope of the tangent line when x is 3, the slope of the tangent line when x is 4. You can see how that can get kind of redundant. Wouldn't it be easier if we could just find the derivative function and then plug in x is 2, x is 3, x is 4, and get those values, those numbers we're interested in, okay? So again, this is another thing students kind of get confused about. So they say, well, sometimes the derivative is a number and sometimes it's a function, and I'm not sure which, okay? If you're evaluating it at a particular x, you're going to get a number. If you evaluate the derivative in general, it's a function that turns out those numbers for given x values. Okay, and those numbers, again, are the instantaneous rate of change of the function at that x, slope of the tangent line at that x, or the marginal value of the function at that x. This last one is going to be the most interesting to business majors, okay, because it's going to help you do applied problems. If you see an applied problem and you have a function that's asking for marginal value, you're going to know I need to take a derivative here. Okay, so that's kind of how it's going to help. All right, how we doing so far? Questions, anybody? You good? All right. Let's talk about some notation. And again, these notes are excerpted from your textbook. Okay, so please, I would encourage you, go and read the textbook anyway, because these notes don't contain everything that's in your text. But I try to hit the high points. Okay, so I'll usually put these yellow boxes that are in your text that have important information. Okay, so again, this is reiterating what I kind of just said. Derivative is instantaneous rate of change, slope of a tangent line, right? A function is differentiable if you can take its derivative, okay? And it turns out you can take the derivative of a function if it's continuous there, which is why we talked about continuity before, okay? So again, I'm trying to show you how all this stuff fits together. All right, so here are a couple of different notations for derivative, okay? The derivative of y equals f of x with respect to x. So again, x is your input variable, y is your output variable. You realize I could also take the derivative of v of t, which is a function velocity with respect to time. There I'd be taking the derivative of v with respect to t. T is your input variable. And the reason why it's important to identify it, you might be saying, yeah, all right, so it's the input variable, big deal. It's either t or it's x. That's true, but there's also calculus that involves functions of more than one variable. We won't be talking about them in this class, but we will in MAT213. So you have to discriminate which input variable is the one that's changing, okay? So that's why with respect to the variable, input variable is important, okay? So here's the different notation. We have f prime of x. That's the way you would read that. It looks like a little apostrophe, okay? So f prime of x, and that's on your keyboard. It's below the double quotes, okay, right next to your enter key, okay? You can also read it as, if you've not got function notation, if you've just got a y, you'd say y prime, okay? So whenever you see this little apostrophe, call it prime, okay? This notation is called differential notation. And again, there's two different notations invented by two different people who were working on it at the same time. Most times I will use the prime notation because I think it's clearer. But there are going to be applications where this differential notation is more helpful, okay? So this is written as dy dx. And you can see it's in the form of a slope, right? With the d, the change, delta in y, over delta in x, okay? And again, this is going to be useful when we want to know what variable is the input variable. Okay, so this has the x right down here and we can see it. Okay, so again, dy dx or df dx, more commonly like this. Okay, this is called Leibniz notation after the mathematician who invented it. Okay, and like I said, it's useful because it shows you the variable that we're differentiating with respect to. Okay, so again, it's just a slope, nothing fancy about it. Okay, so again, you'll see both notations, so it's a good idea to be comfortable with both notations. Okay, here's some more information. Okay, we talk about taking a derivative. Okay, there is a verb called differentiate that we can use as well. It means the same thing as take the derivative of a function. Okay. You might also see, and you will definitely see this in online apps if you use them, okay, d dx of f of x. Okay, what does that mean? That means take the derivative with respect to x of the function f of x. So it means the same thing as df dx, and it means the same thing as f prime. Okay, so all of these notations are swirling around out there. Okay, and it's definitely a good idea to at least be comfortable with these two. If you use stuff online, you're going to see them all. Okay, and again, I want the tools that are out there to be useful to you. So in order to make that happen, you've got to be fluent in the vocabulary of taking a derivative. Okay, so again, we're not going to go through a proof of anything, but I just want to show you the formal definition of a derivative. Okay, here it is. It says the derivative of f with respect to x, or f prime of x, is the limit as h approaches 0 of this quotient. Okay, and what's this quotient? Well, that's exactly the slope of a secant line. Okay, so limit. Let's put it this way. Limit of a difference quotient. Okay, this fraction is sometimes called a difference quotient. Why is that? Well, it's got a difference in the top. And if you think about it, there was a difference in the denominator, right? It was x plus h minus x down here that gave us the h. And then the quotient is the divide operation that happens between the numerator and denominator. So sometimes people will call this a difference quotient. We're taking the limit of it. But what is it? Okay, this quotient is nothing more than the slope of a secant line. Okay, so a practical definition of the derivative is an approximation, right? It can be approximated by looking at the slope of the secant line over a really tiny interval where h is getting close to 0. Okay, that's the practical definition. Okay, so again, what we're going to be doing eventually is using some formulas to calculate the derivative quickly. But again, you ought to be able to do this from a graph, okay, from a table, okay, and in order to do that, you're going to have to use this approximation, okay? So if you have a function rule, we can use our formulas. If we don't have a function rule, if we have a graph or table, we're going to have to use this definition, okay? So anybody got questions about notation, about vocabulary or notation? Anybody questions about vocabulary or notation? Okay, good. Okay. Again, feel free to just give me some feedback, okay? No problem. All right, let's take a look at some examples then. All right, and again, we're going to start with an application that's really common. It's throwing something or launching something up into the air. Okay, so this is going to be the height of a rocket. The function that describes its height is called h of t. So that tells you h of t, the height, is your output. T, time since it was launched, is your input. Okay, so it says we're going to show the graph of the height, sketch the graph of the velocity. Okay, now velocity is the derivative, it's the rate of change. Of height with respect to time. Okay, it's a rate. So it has rate units, right? It has output units, which are going to be in feet, let's say. And the time units, which I'm sure for a rocket are going to be in seconds. Okay, and these are velocity units. Okay, so again, everybody should be comfortable with the fact we're building a slope formula. Slopes have units, output units divided by input units. Okay, so let's look at our picture. Okay, so I have the height of my rocket in feet. Okay, and it looks pretty much like you'd expect height to look like for something that was launched. It eventually gets up to a certain height, and then gravity starts acting on it. And well, gravity's acting on it the whole way, but at this point, its initial velocity can't overcome gravity anymore, and it starts coming down. And notice this weird little break right here where it goes from coming down like a rock, okay, and then it has more or less like a constant descent rate, okay? Usually with a rocket has parachutes on it, okay, and at some point maybe the parachutes deploy, okay, so the rocket doesn't crash, it comes down slowly. Right? Just so you know what that weirdness in the graph is. Okay, so let's take a look at what we might notice about this graph. First of all, let's imagine we're looking at tangent lines to the graph. You can see the tangent lines have positive slope as we go, as the rocket's climbing. Okay, before it reaches its maximum height. Okay, so the tangent lines have positive slope, and you can see that down here. Okay, what's important to realize is right here up at the top, okay, the slope is 0. Okay, so at the rocket's maximum height, the tangent line has a 0 slope. That's going to be really important. Okay, it's going to help us find those maximum and minimum values of a function really quickly. Okay, now a lot of you might say, well, if it's a quadratic, I can find the maximum. That's the vertex. That's minus b over 2a. I can do that really fast. That's true. Okay, but not everything is going to be modeled by a quadratic. Okay, some functions are going to be more complicated than that. And calculus is a really easy way, okay, to find the maximum and minimum points. Okay, don't also forget that some functions are hard to graph. They're hard to see where the maxes and mins are, but the calculus will tell you pretty much right away. Okay, so I'm trying to give you a sales pitch as to, why would I want to do this? Okay, so again, you can see, okay, on this graph here, they've drawn the original function, height versus time. That's the blue line. And they're showing you the slopes of the tangent lines. Now, here's what I want you to notice down here, the red graph, okay? They're graphing the slopes of the tangent lines, okay? So here I have a really large positive slope, you might be able to tell this one is not quite as large. Okay, the slopes are getting smaller. Okay, they're positive, but they're decreasing. Okay, does that make sense to you? So if I were to graph the slopes, you're going to get a series of positive but decreasing values. Okay, right at t equals 5, the slope is 0. Okay, so I have slope equals 0. And down here I have y equals 0. Because what am I graphing as y? I'm graphing the slopes. Okay, now what's happening? Well, once we get over the bump here, you can see the slopes are negative. They start out being small negative numbers, and then they get more and more negative. So look at what happens to the graph of the slopes down here. It goes below the x-axis because the slopes are now negative values. And then right here, there's this sharp bend, okay, where the slopes go from being really negative to being slightly, well, less negative, and then they stay the same. I think you can see this is going to be a straight line, okay? So there's a break in the graph right here, okay, and that's at t equals 8, okay, when the chutes deploy on our rocket. And there's a discontinuity in the graph of the slopes because they go from going straight down to now being a constant value, okay, which is kind of what you want if you want your rocket in one piece. Okay, so the question I'm asking you is, does the red graph make sense? Does the red graph make sense? Okay, can you just give me a yes or a no here? Okay, does the red, so again, the y values on the red graph are the slopes of the tangent lines on the blue graph. Okay, another way to look at it is the red graph, v of t, this is v of t, is the derivative of the blue one. Okay, so this red graph down here is the derivative of the blue one. Okay, so if the red graph makes sense, I'm going to share another applet with you that's in week 3 of our course, and it's a derivative plotter. And let's see where that is. I think it's right underneath the toolbar. Okay, so just give me a second to see if I can get this out of the way. Applet slope of the secant line. Nope. Derivative plotter. Sorry, it takes a minute for the toolbar to recede, and then I can show it to you. Whoops. Every time I go up, it comes back. Here we go. All right, so here's our derivative plotter. And again, you can see I've got y equals x squared plotted as my function, and they've got the graph of the derivative below it. And again, what you want to imagine is what I'm showing you on the top is the slope of the tangent line. You can see the tangent line. And then as the cursor comes up the red line, it's plotting that value. You can see right here, the slope of the tangent line is 0, and I'm right at the origin in my red graph. And likewise, coming up this side, now the slope's positive. So now my derivative graph is above my x-axis. You can put whatever values you want in here, so you can make things more interesting. That's not more interesting. That's more interesting. Okay, so take a look. Now I have a 3rd degree equation. I'm going to come up this side. So positive tangent line. And again, you can see right as I get here, I still have a positive tangent line, but it's getting less and less steep. So the values are coming down. And right at this high point, I'm at the x-axis. I have to be a horizontal tangent line there. It's a little tough to get it just perfect, okay? But you can see when that tangent line's horizontal, I'm right at the x-axis on my derivative graph. Now my tangent line's negative, so I'm below the x-axis. Okay, right here I've got another low point. Okay, so I'm basically again at the x-axis, and then it's positive all the way. The other thing I want you to notice is, see how the graph of the derivative looks like a quadratic. Okay, see how the graph of, I have a cubic up here and what looks like a quadratic down there. It's like 1 degree less. Okay, that's going to be important when you're using formulas to find derivatives. Okay, that's not by mistake. That's not coincidence. It happens that way. Just like in my example, this part of my graph looks quadratic and my derivative looks linear. Again, 1 degree less until I get to this discontinuity over here. Okay, so as long as this makes sense to you, let's take a look at approximating slopes of tangent lines. Okay, so how might you do this with a table? Well, here they're giving you a graph. They didn't give me a function rule, so I can't use the limit of the slope of the secant line. I have to kind of approximate at different points along this graph. So they give me some x values. So I have 0.5, which is going to be like here, 1, 1.5, which is about here, 2, 2.5, 3, 4.5, and 4. Okay, so I've got a bunch of points and I kind of made dots on the graph. Why did I do that? Well, I'm going to try to approximate what those y values are at that point. Okay, at 0, it's pretty obvious my y value is 1. I'm sitting right on my y-axis. At 0.5, I'm guesstimating that's a little bit below halfway up to the next whole number. So I'm going to say 1.3. Okay, if I look at where I am at 1, let's call that 1.5. Okay, although it might be a little higher than that. Looks like I came back down to 1.3 at 1.5. Okay, 2, it's pretty obvious. I'm at 1 again. And 2.5, I am sitting right on the x-axis, so the y value is 0. At 3, I'm at -1. You can see the graph's dropping pretty fast right here. You can see by looking at the changes in the y values. Okay, then it looks like I'm down at -1.5. And by the time I'm at 4, I'm back up to -1. Okay, everybody comfortable with how I'm approximating those y values? And yes, it's an approximation. Okay, now if I want to figure out the slope, okay, what do I have to do? Okay, slope of the tangent line, I have to kind of estimate it. Okay, how might I do that? Okay, well, you might do something like y2 minus y1 over x2 minus x1, and then take the limit of it. Okay, you can also kind of eyeball your slope here. Okay, I might say the slope right here at 0 is 1. Okay, I'm approximating it by saying, well, if I were to draw a tangent line here, it would probably look like that. It's slightly less than that here. Okay, by the time I'm here, it's a 0. Okay, so these are approximations. And again, you can do it by actually computing out the slope and taking the limit. But I just want to do a quick and dirty thing to show you. I think everybody can find the 0 values, right? The 0 values are going to be where the graph turns around. Okay, so that's going to be at x equals 1 and at x equals 3.5. I'm going to have 0 values. And the slopes are fairly smooth. Okay, so I have positive slopes going up to that first one. Then I have negative slopes, shallow ones, then steep ones, then even steeper ones. Okay. Then they get shallow again. Okay, so I'm kind of approximating here. Okay, the steepest slope on this graph is right here at 2.5. Okay, the graph is really taking a dive right there. Okay, so those are my best guesses for approximating the slope. Okay, now again, if I plot these as y values with the x values, okay, so basically I'm looking at the y values and I'm plotting them with the same x values. Here's what I would get. Okay, so I'm looking at that same table and I'm plotting the point 0, 1. Okay, then 0.5 and 0.5, that's going to be here. The next point is 1, 0. Okay, the next point is 1.5 and negative 0.5. Okay, and the next point is 2, negative 1. And then I have 2.5, negative 1.5. I have to kind of go down here. Okay, then I have 3, negative 1, 3.5, 0, and 4, 1. Okay, so the dots I just plotted, folks, are ordered pairs that use the y values here and the x values here. Those are the points that I just plotted. And again, if we connect those, and here's the interesting part. Let's see if I can hit all of these points. Okay, I have a graph of my derivative. Okay, so this is a graph. Okay, so it's a derivative of the red graph. Okay, and again, how do you tell? Well, you can basically see positive but decreasing slopes. Here's the slope is 0. Wherever you have a turnaround point in your original graph, your derivative graph will cross the x-axis. Okay, so I have one turnaround point here. There's my y equals 0. Here's my other turnaround point here. Here's my y equals 0. Whenever the graph's decreasing, your derivative graph is below the x-axis. Okay? Everybody comfortable with that? And we'll talk about what it means to go from decreasing to increasing here. Like, why does it turn around and come back? Okay, we'll talk about that. All right, so right here, the graph goes from decreasing, it's decreasing all the way, but it goes from what's called concave down to concave up, and that's why the graph turns around here. We'll talk about that. Okay, but does everybody at least understand generally the derivative graph crosses the x-axis when the original graph turns around? Okay, everybody good with that? Everybody see that? Okay. So this maximum point will give us a derivative of 0. This minimum point will give us a derivative of 0. That's going to be important. So I want to make sure everybody sees that. Okay. All right. Now what I'm going to do, I'm not going to do another table one here, but I just want to look at the graph. Okay. And I want to ask you the question. Okay. For example 3, where does the graph have a horizontal tangent? Okay, and I'm asking for an x value. Where does it have a horizontal tangent? Okay, everybody see it? Okay, so we're looking at example 3. Where does this graph have a horizontal tangent? There might be more than one place, so just give me the x values. Okay, so we're seeing here at 1, here at 3, and here at 4. Okay, so x equals 1, 3, and 4. And where is the output value of the function the largest? Okay, so which x value is the largest output value? Okay, by output value, I mean y. Yep, 4. Okay, and how about the smallest? Yeah, okay, that would be at x equals 3. Okay, and again, the same idea. If you were going to graph the derivative of this function, you would know you would have a derivative graph that would have a 0 here, a 0 here, and a 0 here. Okay, again, increasing slope, but getting smaller, like this. Okay, and basically you can see you'd have it do something like this, come back up. Okay, you can see what the derivative graph would probably have to look like. Okay, again, I'm not going to go through approximating the slopes again because that's kind of tedious. Okay, although I can show you that it would look like this. Okay, and again, what I want to make sure you understand, if we go back to the derivative plotter, if you've got a function rule, you can actually see what your graph of your derivative looks like. Okay, so don't hesitate to use not only this stuff, approximating the slope at a tangent line, okay, but also use the apps I've given you. Okay, so there are a couple of examples that look like this. All right, this is the same example, so I'm gonna go down to this one. And don't worry, I'll fill in the notes so you have all the information. Let's take a look at this one. Okay, example 4. Where are the horizontal tangent lines? Where are the horizontal tangent lines in number 4? Okay. Anybody else have any ideas? Can everybody see the graph? Yep. Yep, we've got a horizontal tangent here, here, and here. This is kind of iffy exactly where it is, but again, it looks like it's a low spot, so we'll say it's 3. Again, the largest value is where? Where's the largest y value? Okay, and how about the smallest? Okay, I agree. The largest value is X is 2. Yeah, if you look at the graph, you can see your output value, your Y value is slightly smaller than 1 here. It looks like it might be sitting right at 1 here. Okay, so I would say X equals 1 now. Okay, and then the same idea, graphing the slope. If we want to do it right on this graph, let me get rid of my horizontal tangent lines. And everywhere my tangent's horizontal, I'm putting a dot on the x-axis because that's where my derivative graph is going to cross the x-axis. Okay. Now notice here, your graph has a negative tangent line here, right? So it's sloping down, but it's getting somewhat less negative till it hits 0. That means your derivative graph, okay, the y values are going to be below the x-axis. Okay? And again, don't worry about being an artist. Okay? If they ask you to do any of this in the homework, I'll have to grade it manually. Some of you found those questions. There are some questions where you have to draw a graph. It's not going to be graded until I look at it. I mean, there's no way to have software look at a picture yet and decide whether or not it's correct. So don't worry about not getting points for those questions. Once the due date for the homework passes, I will grade those manually. Okay? So then you can see at some point, now we have an increasing function. At some point, we're going to wind up turning around and coming back down to that one. Okay? Slope is negative here. Comes back up. And then it kind of looks like maybe the slope is sort of constant from here on out. So maybe it increases and then maybe it's kind of like this. Okay, constant slope. Again, if you've got something that looks like a straight line, that means the slope of a tangent line is the same thing as the slope of a line. It's not changing. Okay, so you can kind of see my attempt at graphing the derivative. Good idea is to always start with the turnaround points, put the dots on the x-axis. Okay, and again, I'll work all of this out for you, not to worry. I just don't want to take the time when we're actually in class guesstimating slopes. It's tedious. Okay, as long as you understand the concept. Okay? So understand how I'm getting the derivative graphs. Okay, I want to make sure we do a couple of algebraic examples so you can get the drift. Okay, all righty. Let's take a look at, this is something that is really useful. I'll show you down here, example 5. And again, I may need to minimize the chat to get it out of the way. Let's see if I can move it somewhere where it's not blocking the view. Okay. This is kind of a classic in intro calc classes where they show you 3 graphs. Okay. Let's call them, they didn't label the bottom one, so let's call them D, E, and F. Okay, and they tell you that match the story with the time velocity graph. Okay, so what they're telling you is all of the horizontal axes are time and all the vertical axes are velocity. Okay, this is a classic. Sometimes they'll do it with position and time, so you have to pay attention to what it is that you're trying to figure out. Okay, so they give you some descriptions and then they want you to try to say, okay, what graphs go with what stories? Okay, so let's take a look at some of these. Okay, if a car leaves slowly from a stop sign, okay, imagine it's just like rolling along. Okay, which graph do you think that would be? Okay, what about a student? What about leaving quickly from a stop sign? Bouncing on a trampoline. Remember, you're not looking at position. You're looking at their speed. okay? A ball thrown straight up, a student walking across campus, assuming the student's walking at a constant rate. And here's an unprepared student. You would imagine this student would hesitate, might turn around, might, go fast, then go slow, not really sure they want to get to the classroom. Okay? So take a look at these graphs for a minute. And see if you can figure any of them out. See if you can match any. Okay, we'll take a few minutes for you to do this. Okay? If I were you, I'd start with the straight lines. See if you can figure out which stories match those. Okay, if you remember, over here you've got numbers, and over here you've got letters. So any one have a number, letter match. Okay, anybody have just one? Just share one that you think match. Anybody have a number, letter match? Share one of them. You don't have to share all six. Okay, so Julian's put one in. Anybody have others? Ornella put one in. Okay, Jacob has one in. And Nee has one in. Okay, great. These are hard. I'm not going to kid you, okay? The ones with position are a little easier, but velocity is kind of hard because you have to figure out how's the velocity changing in the story. I suggested start with the straight line ones, and I noticed a few of you did. Okay, how about this? This essentially, let's look at C. C is a constant velocity graph, okay? So a student who's confidently striding over to their class, okay, because they know they're prepared for a test, is probably moving at a constant rate. So I would agree that 5 goes with C, okay? Again, not speeding up, not slowing down, okay? This one, again, everybody has seen the position graph for number 4, okay, with the quadratic, okay, where the position of the ball starts at 0, goes up to some high spot, and then comes back down to 0 again. But that's a position graph or a height graph, okay? A velocity graph, think about what happens to the speed of a ball, right? It's the fastest when it leaves your hand, okay? Positive velocity is away from the starting line, okay? At some point, it's getting slower and slower and slower. See the velocity coming down. And right here at the highest point in its trip, it has for an instant a 0 velocity. It hangs there for an instant, okay? And then it starts coming back down. So that means the velocity gets more negative. but it gets larger, negative, right, as it comes back down. Okay, so this is the velocity of your ball being thrown straight up. Okay, some of the other ones folks said, let's see, the trampoline one. Okay, so you jump up first, right? And your velocity is kind of like the ball. It gets lower and lower till you hang up there. Then you start coming back down again. And again, what's the key here is the regularity of these. Okay, so I think that E is the trampoline one, is number 3, right? Okay, what other ones did we get? Somebody said we had B, C, E. Somebody said D. Okay, D is kind of our unprepared student. Okay, so maybe our unprepared student has a positive velocity, but then decides I'm going back. Well, maybe I should stop and think about this. All right, I'll go to class, but maybe I'm stopping over here and I'm going back. Okay, so this is the changing my mind and turning around. Okay, but it's not a regular graph like the trampoline. Okay, so it shows a certain amount of hesitation. So I'd say that's D. Okay, so we have our stop sign situation. Those are the only 2 that are left. Okay, a car leaving quickly from a stop sign. Okay, so positive velocity. Okay, and then maybe at some point you start driving at a constant rate. Okay, so positive velocity, but getting faster. Okay, so you can see we've got a positive upward curve here. Okay, here's a slower trip away from the stop sign. Yeah, you're increasing, but not all that fast. Okay, so I would say that A is number 1, and I would say F is number 2. Okay, anybody got questions about these? Okay. Again, the trick with doing them is try to understand what's going on, try to model the situation in your mind. But again, yeah, it's a silly matching exercise, but again, if you're actually doing it, I think I have one of these like a discussion board problem. Try to explain your thinking. Okay, that's really where the value of these problems come in, is if you talk them out. Well, I thought about this one because again, it starts out going upward, but then it goes upward slower and slower until finally it's hanging there right at the top of its trip. And then it starts coming backwards. Okay, so you get a chance to explain to someone else here. Imagine you are actually tutoring somebody and they don't understand and you need to explain it to them. If you can explain your thinking, you really, really understand it. Okay, so I know a lot of students resist that because their attitude is, well, you know, I got it, I'm good. Try to explain it, even if you wind up trying to explain it to your dog. I know the dog's not going to look at you kind of like funny, but it's good practice. If you can put it into words, that means you really understand it. Okay, so that's kind of the logic behind some of my discussion board problems is I ask you to put your thinking into words. And to be honest, if you're doing any kind of math related stuff in your career, okay, that's how you're going to figure out if your answer is right. Remember, there's no answer key. So it's you trying to explain your reasoning to someone else who tries to explain his or her reasoning back to you. And together, the group comes up with the best solution. And that's the product of everybody's reasoning. Okay, so please don't resist it. It's what you're going to have to do when you get out there. Okay, so finally, we have a calculate 1. Okay, so let me show you how this works. Okay, so again here, I have my function f of x. It's a linear function. And again, if you remember, I have to figure out my slope of the secant line that's just h units away from some point x on the graph. So in order to do this, I have to calculate f of x plus h. How do you do that? You plug in x plus h everywhere you see an x. okay? And then again, remember what this was down here. This was okay, x plus h minus x. Okay, so it's the change in y's over the change in x's. Again, remember, slope of the secant line. Okay, and that's just going to give us f of x plus h minus f of x on the top. Okay, so f of x plus h I figured out. Okay, and then I have to subtract f of x. Now notice my f of x has two terms in it, so please make sure you put them in parentheses. Okay, and then I have my x plus h minus x. That's just going to give me h on the bottom. Okay, everybody see where these expressions are coming from. See where the expressions are coming from? Anybody questions about what I plugged in over here? Okay, anybody issues with it? So all I did was the x part, you don't have to worry about. It's x plus h minus x. It's always h in the denominator. The f of x is going to change depending on the function rule. So you need to calculate what is the expression for f of x plus h. That's what I did over here in my work area. And I plugged it in over here. Here's f of x plus h minus f of x. Okay. Then all I need to do is a little bit of algebra in the numerator. I'm going to distribute that negative sign. That's going to give me minus x plus 7 over h. And if you look at this, the 3 x's cancel out. The 7 and negative 7 cancel out. And I get 3h over h. My h's cancel out. And that gives me 3. Okay? So notice I started with a linear function. Let me ask you a question about this linear function. Okay, see it up here, f of x? What's the slope of the linear function? Yeah, f of x has a slope of 3. See it right here? Does the slope of a linear function change as you move around the graph? No. Okay, linear functions are defined by a constant slope. And look at what you got. You got a constant slope. Okay? So the slope of a secant line and the slope of a tangent line to a linear function are exactly the same thing. They're constants. Okay, because a linear function has a constant slope. So if I take the limit as h approaches 0 of 3, anybody see any h's in there? There's no h's in this expression. So it's 3. Okay? Don't be concerned by this. Okay? I can hear a lot of folks saying, wait a minute, why is she taking the limit as h approaches 0 when there's no h's in the expression? Because that's the definition of the derivative. If there's no h's in the expression, we're good to go. Okay, we got a constant slope. The limit is still that same constant. Let's do one that's a little more interesting. Okay, so I have another example like 6 with a quadratic function. Okay, so here's my slope of my secant line. G of x is my function. The first thing I'm going to do is find g of x plus h. And everywhere I see my x, I'm going to plug in x plus h. So there's x plus h squared. I'm going to back up a little here. Sorry. Otherwise, I won't have enough room. So this is g of x plus h. So x plus h squared minus 7 times x plus h minus 18. Okay, so the first thing I'm going to have to do is square the binomial. You can do it with FOIL, or you can use that pattern I showed you, which says square the first term, square the last term, multiply them together. That's x times h, and it's positive, and then double it. That goes in the middle. Okay, that's a shortcut for squaring a binomial. Next, I have to distribute my -7 across this other binomial. Okay. And then I have to take a look to see, all right, nothing cancels out there. I've got x squared terms, xh terms, h squared terms, plain old x, plain old h, and constant. Nothing cancels. So now I get to plug it into the secant slope formula. So this whole big mess goes in for g of x plus h. Right, so I want to make sure I copy it correctly. Okay, so there's g of x plus h. Okay, and now I have to subtract g of x. So again, g of x has multiple terms in it, so it needs to go in parentheses. And the whole thing's over h. Okay, everybody good with the g of x plus h and the g of x? Okay, if you want to, again, I'm writing it out just for clarity. You don't have to do all the copying if you don't want to. But I'm just doing it to show distributing the negative sign. Okay, that flips the signs on everything inside. And now let's look at what cancels out. I have positive x squared, negative x squared. I have -7x, positive 7x, -18, positive 18. Okay, I strongly urge you, if it's been a while since you've done algebra, write everything out. Okay, and give yourself plenty of room. Don't jam it in. Okay, it's a lot easier to do it once with multiple steps than to do it over and over and over. That's frustrating. Okay, so give yourself plenty of space. So what am I left with? I'm left with 2xh plus h squared minus 7h over h. Okay, those are all of the terms that are left. You might be able to see, oh, hey, divide out an h. That gives me a 2x, an h, and a minus 7 on top. Okay, so I've factored out my h. So my slope of the secant line, 2x plus h minus 7. Okay, is everybody okay with this? With the algebra? Okay, is everybody okay with the algebra? Take a look at it. You're going to have to do the same thing. Okay, I'm just asking, everybody good with the algebra? Anybody have problems with it? Okay, so now that's the slope of the secant line between what? A point, you know, xy and another point x plus h, and however far away that value is. Okay, so what do we have to do to find the slope of a tangent line? We need to take the limit as h approaches 0 of the slope of the secant line. This is the slope of the secant line. So I want the limit as h approaches 0 of this. What do you think that value is going to be, folks? Okay, so what's the value? Yeah, 2x plus 7. Everybody see it? You can just plug in 0 for h. Okay, this is an example of finding the equation of the derivative. Remember we spoke about that initially, where we talked about the derivative at a particular value is a number, it's a slope, right? This just asked you to find the slope of a secant line, but it didn't give you a point. Okay, so it's asking you to come up with an expression for the slope. Okay, and that expression is 2x plus h minus 7. Then take the limit of that expression as h approaches 0. This is the derivative of this. So another way I could put this is g prime of x equals 2x plus 7. Okay?
Should it be minus 7?
Is it minus? Yes, minus. My bad. Thank you for finding that. Good
no problem.
You. Thank you. Minus. Appreciate it. So yes, it's 2x minus 7. And what that is it's a function that will generate the slope of a tangent line as you move around g of x. Okay? Notice g of x was quadratic. G prime is linear. It's dropped by a degree. Everybody see that? Okay, and that's the same thing you'll notice when you draw the graphs of the derivative. Okay, if you start out with a quadratic function, your derivative graph should look linear. Right? All of that stuff should, hang together. Yeah. All right with that? Okay, so let's just look at one last thing. Okay, take a look at these. Okay, here I have functions on the top in blue and derivative graphs in red. Okay, see if you can do this. Okay, these have letters on the top, F, G, and H, and letters on the bottom. See if you can do this. See if you can match the graphs with their derivative. See if you can match the graphs with your derivatives. Okay. Type 1, matched pair, and you're done. Okay, so type 1 matched pair once you're done. Again, let's turn around points first. We have one contender. Anybody want to try any of the other ones? FC. And by process of elimination, that leaves what? B and H. Okay, so let's take a look at your choices. Okay, let's do the quadratic one first. Okay, I have a positive slope, but it's getting smaller. And then I should have a 0 slope right here. Okay, only one of these graphs ever hits the x-axis. Okay, so I agree that A and G match. Okay, and then you can see the slope here becomes negative, so the y values on the derivative become negative. Okay, let's look. Anybody questions on A, G? Okay, this is interesting. If you're looking at this graph, you see these massive discontinuities. Okay, that tells you that your original function graph jumps around. Okay, something happens to its tangent line. Well, let's take a look at F. Okay, it's a bunch of linear graphs that are kind of stuck together, right? If you think of it that way, constant slope, constant slope, constant slope, massive break-in slope. So it goes from being a positive constant right here to a negative constant. Okay, when it flips over this cusp. Okay, positive constant, whoop, negative constant. All right, with a discontinuity right at the cusp. And then it flips to being a positive constant again. Okay, so yes, I agree that F and C match. Okay, the other choice, okay, is G and B. Okay, let's take a look. Not G, my bad. Okay, it would be H and G and B. Okay, so you can see we have a positive slope that gets steeper. Okay, and at some point in here, we have a switch from increasing, going concave up to concave down. And then we have slopes that are turning around again. Okay, so that's this one. Okay, the ones with changes in what are called concavity, cupped up to cupped down, you don't know how to see those yet. So those are pretty much going to be the one that's going to be odd man out. And once you pick everything else, that's the one that's going to be left. Okay. All right, so anybody questions on any of this? The part you want to make sure you're comfortable with is, plugging in to that difference quotient formula and taking the limit. Okay, it's almost all of it is algebra. Okay, but I just want to make sure everybody's good with that. I'm going to come back to our meeting. Okay, and ask again. Is everybody all right?